at Jindal School of Government and Public Policy and wider academic community at our university and also beyond, as we are being joined from various other noted universities across countries. So myself, Professor Sudeep Patra from the Government and Public Policy School, and also Complexity Economics, Applied Spirituality and Public Policy Research Center. So we are very glad to organize another session on our ongoing open lecture series, where we are very glad to host eminent researchers in various fields related to policy research. Today we have Dr. Thomas Hancock with us from Leeds University, UK. He is an award-winning researcher for his thesis at Leeds University, and he's based at the Choice Modeling Center at Leeds University, which is an interdisciplinary research center bringing on different methods from statistical as well as natural sciences to extend that to human decision-making problems. For example, quantum-like modeling, which Thomas is working in for some time. And this has also been one of the areas at our research center here. So earlier we were also glad to host Thomas for a couple of seminars. Today Thomas would be kind of presenting us his new works, ongoing works on transport choice or choice behavior of decision makers in terms of transportation, mainly in the context of uncertainty, ambiguity, and others, using novel methods like quantum-like modeling. And here we'd also be very keen to see that what policy implications can be there based on robust data sets that they are working on. So without further ado, I will request Thomas to take the stage. So the talk might be overall about 40 to 45 minutes, and then certainly about 15 minutes question answers. As the talk is on, we can post our questions and comments on the chat box. So thank you, Thomas, for coming again. And please, if you take the stage.
So I'll start by sharing my screen if I can. I can't currently share.
There's a green share button, I think. Share the screen.
Yeah, I've got, it says host disabled. Sorry. Sorry, it says host disabled. Is the host able to enable distance?
That's all right, Thomas. IT is with us. They will.
All right, perfect.
Hi, everybody. Vikas, if you're there, please, can you give him the...
He has got the access.
Okay, okay.
Yeah.
Thank you.
Yeah, thank you.
Right, so can you see my...
Yeah.
Now. Perfect. Okay, so hopefully this is in full screen mode for you. You can see this in detail. Right, so hi, my name's Thomas Hancock. Thank you very much today for the introduction. So I don't need to say too much more, but this is what I've done mostly with my supervision from Stefan Hess and Charisma Shattery, who are my PhD supervisors, and also our colleague Jan Broeckert, who was our, I guess he was the sort of real quantum guy of our group. He came from a background of quantum physics, and we merged his knowledge of quantum physics and our knowledge of choice models to come up with these quantum choice models. So today I'm going to focus on how these models can capture changes in choice contexts. And I'm going to give a sort of brief outline of how we can set up the codes for this as well, just to show you just how simple it can be to actually set up these models. So just a presentation outline. I'm going to give a brief introduction to choice modeling and what we actually regularly do at the Choice Modeling Center. I'm going to talk about what I mean by a change in choice context. I'm going to talk about some typical choice models before then talking about quantum choice models that we've developed. We have a few case studies in the applications, and then I'll talk about some next steps and conclusions. firstly, brief introduction to choice modeling. So there's a number of different reasons why we might study decision making, and there's a number of different disciplines that do this. So mathematical psychologists would really look at the decision making process. They want to know how the brain works, how are we processing information, how do we integrate the different sources of information, and how do we then come to some decision. Choice model is a slightly different focus. It's more about prediction and forecasting choice behavior, which you can probably imagine that has sort of very relevant implications for policy. Decision optimization is what decisions research do. So they are looking more at how do we make the best possible decisions. Whereas within choice modeling, it's more looking at what people actually do and what they actually choose, which may not always be the best choice. People often make silly mistakes or do something that looks quite random. Understanding how the brain encodes, evaluates, and chooses options. This is more sort of neurobiology. So a lot of people are interested in decision making, and all of these are going to be important in the context of business studies. But choice modeling is more at the front of informing policy. So what actually is choice modeling? To put it simply, it's building a mathematical representation of the decision-making process. We're going to use this mathematical model to generate probabilities that a decision maker will choose different possible alternatives. So we'll have some set number of alternatives that someone can choose in a given scenario, and our model will predict the probability that someone will choose the option that they do. We're going to use econometric and psychological theory to build this mathematical model. So what I'm saying there is that we've got certain assumptions that or things we might expect, which we can then use to try and make our model as accurate as possible. So what do choice modelers actually use these models for? So the main thing we do is we put prices on things that do not have explicit prices. So what I mean by that is, for example, time. There is no currency with time. So we estimate willingnesses to pay for certain goods. Time is an example, green spaces, safety, value of life is another good example. And you can see how across different disciplines, there's different things we could use this for. And this is partly why choice modeling is so interdisciplinary. And across the world, all choice modelers are in various different departments because we do very interdisciplinary work. And some are very focused on specific elements. So you might have a health choice modeling group. We're ourselves based in the transport department in Leeds University. So the key thing that we do is we rely on choice data rather than contingent valuation. So in contingent valuation, you have a direct estimate of what someone is willing to pay for. And this is subject to a lot of biases. So for example, if I say to someone, you're going to take this train and it will save you 30 minutes, how much are you willing to pay me to save those 30 minutes? That is going to be subject to a lot of biases, context, how the person's feeling on the day. And you can get a better estimate and more accurate estimate by presenting choice scenarios, so hypothetical choice cases. So I'll talk about a few different ways of collecting data that we use in our choice models. And then we use these choices to forecast future scenarios to inform policy. So for example, if I want to reduce the number of cars in the city, maybe I can do a hike on petrol price, and we can have a look with our choice models how that might actually, what impact that would actually have. So if I say we had a 10% increase on petrol price, with what percentage of people might then change which modes they travel by. So this is the simplest way of understanding preferences is a stated preference task, something like this. So imagine you're in this scenario, you've got a few different alternatives. Your first alternative is to have the same travel time, the same salary, or you move to an equivalent job where everything else is the same, except your travel time is now 10 minutes longer and the salary is 1,000 kronas more. So this was from a case study in Sweden. So it's about a bit over $100 more per month. So you could choose the two different alternatives, or you could say you're indifferent, and you could present a number of people with similar tasks to this, and then these numbers would change. So you might have different numbers there, and you get an idea of what that travel time journey is worth to them. So how much time they save and how much they're willing to earn for that. So basically, is 10 minutes more commute time per journey worth 1,000 krona per month? And multiple respondents' choices here give an observed probability of this new alternative being accepted. So for example, we might observe that 50% of respondents say yes to this. The respondent may value these equally, so that would be when they're indifferent. So they're saying, actually, I don't mind between these two alternatives. I'm going to choose, say, indifferent. And you can also change attribute values. So for example, if it was 5 minutes for 1,000 krona, I'm going to be more likely to accept than if it's 10 minutes more. And it is 20 minutes for 200 krona, then I'm going to be less likely to accept. And we will, of course, observe heterogeneity in preferences. So this is one of the key elements of our research, is to try and understand these differences in preferences. Some people might accept all three, some might reject all three, and of course we'll have people in the middle who accept some of these alternatives. So how do our models actually work? Well, we estimate utilities for each alternative. We do this through estimating the relative importance for income and travel time in this previous example. The model then maximizes the probability of observing the full set of choices. So we've got some relative importance factor for each of the different elements in the model, and we then will come up with some probability of each choice that is completed. So, for example, we might have 10 people completing 10 different choice scenarios, and we've got 100 observed choices, and we're going to maximize the model parameters such that these 100s are maximizing the probability of observing those 100 choices. So what we can then do is compute an average equivalence. So what this means is, what is the average income gain required to offset an increase in travel time? So this is sort of the key, some of the key outputs we can get from our choice models. We can, of course, then increase our model complexity and the flexibility to allow for different preferences across respondents. So, for example, latent class models, different types of respondents. So that's saying that there might be some people who might have two different groups of people with different tastes. Or we could have distributions rather than point estimates of importance parameters. So that's saying that rather than having everyone having the same taste, there's going to be some flexibility and some distribution over tastes. So as well as stated preference, we can also look at revealed preference data. So what this means is actual observed behavior. So the hypothetical element is gone. This is what people actually do. So for example, and here's one data set called the London passenger mode choice data set, which is 81,000 observations of whether people walk, cycle, drive, or get public transport to travel across London. So we've got an example path here. Someone's gone from point A to point B, and there's 4 different routes they might have taken. So there might be different routes depending on which mode they get. So that will mean that the travel times will vary, the travel costs will vary, and the journey comfort will vary, the journey effort will vary. So obviously it's going to take longer and more effort if you're going to walk the whole way. There might be variability in travel time, such as traffic might impact how long it takes by car or bus, whereas the travel times are probably going to be fairly consistent by bike. You might be able to do more if you're on the bus. You might be able to look at emails, work emails, etc. Or you might just want something that's more comfortable and sit in the car. So there's all these different factors that might influence what people end up choosing. But we can try and estimate the various importance of these different factors when we've got a large data set. So RP data has a number of advantages, including avoiding hypothetical bias of stated preference settings. So what I mean by that is that what people say they prefer, they may not always do. So someone might say, oh yes, I would, of course I want to cycle to work. I want to be fit and healthy and not just be sat behind my car wheel. And in the end, actually, they don't have enough time, so they end up driving. So there's always going to be some bias, and there's a lot of work that's actually been done looking at how to mitigate that bias. So then we estimate parameters for the relative importance of these different alternatives. And this is the same. So whatever type of data we've got the same model function. But this means that in an RP context, we can really directly check the implications of policy changes. So for example, how many less choose to travel by train if prices increase by 10%? What will be the impact of petrol price changes in a city, congestion charges, parking price increases, or other changes such as what is the impact of an aging population? Because we might have some information about how different groups of people make different choices. So for example, we might observe that older people are more likely to travel by car. So maybe if we know that our population is going to get older, then we might be able to forecast just how much will change to driving and choosing car. And also impact of increased working from home, which is obviously a very topical and relevant conversation at the moment. So now a change in choice context. What do I actually mean by that? Not what I was just discussing, which I suppose is a change in some way, but what I mean actually here is a subtle change in the current choice scenario that might impact the probability of choosing a different alternative. So basically, I'm referring here to behavioral economics. So a nudge. If someone, what things kind of might influence my decision, and maybe there might be social factors or other things that are kind of not kind of clearly presented in the choice context. But for example, a psychological change in choice context. So an example would be if I'm traveling to work and I have a conversation with someone about how I want to be more healthy, then I may be more likely to choose an active mode the next day. But also we can look at, so here's a change of context, just in this data preference survey. This is a sort of more basic level. So what's happened here is we've got these two choice contexts, but we've got a status quo on the left in the first case, on the right in the second. So in the sort of Western speaking world where we always read left to right, there is usually a left bias where you're more likely to pick the first alternative you choose. But then there's also going to be a status quo bias. So you're more likely to choose your status quo. It's easier to not change. So if we only present people with this first set of choice tasks where the status quo is always on the left, then we cannot separate status quo bias and the left-right bias. But quantum-like cognitive models are great for capturing a change in choice context. So maybe they'll understand how we make choices differently. We have alternatives presented like this or this. And so typical choice models for capturing changes in choice context. I'm going to start with what we have here is utility model. So what we have is typically these relative importances, these betas multiplied by the attribute value. So if we've got just one attribute, then I might have a number of different choice contexts where we've got two different alternatives. And I've plotted here all the various different points where we've calculated utility of the first alternative and the second alternative. So utility is typically a sum over evaluations of different attributes. So example, the importance of cost multiplied by the cost plus the importance of time multiplied by time. And that may give us these various different points here. Now, of course, if you have a higher utility for alternative one, you're going to choose the first alternative. And if you have a higher utility for alternative two, you're going to choose the second. But our standard choice models do not look as simple as this because we have an error. So what we, as choice modelers, do is explicitly assume that there's some unobserved utility for each alternative. So this is from the viewpoint of the researcher. We're saying the researcher doesn't see everything that goes into this decision-making process. Therefore, there's some uncertainty about how these options will actually be evaluated. We've drawn this little line of uncertainty around each of these different choices, and that means that we could land in some choices we might be more certain about, but others may land on choosing alternative one or alternative two. So what we then do is we have this error component within the utility, and different assumptions about the distributional form of this error give us different choice models. So for example, the most standard, most commonly used model is to assume an extreme value distribution type 1 error component here, which gives us the multinomial logic model based on the random utility maximization framework. And this is the really sort of standard model, and it has some nice econometric properties which make it easy to interpret how behavior might change given some change in scenario. So the assumption of this type of error also gives us simple calculations for the probability of each alternative being chosen. So we've got this utility here, which is forms of beta times the attribute value. We just take exponentials to give the probability of each alternative. So and this is the sum of all different alternatives. So j equals 1 to the capital J is the number of alternatives. So that means that the sum of probabilities over all alternatives will always sum to 1, which is obviously the sort of one of the most things we always need in our choice model. We can then maximize the log likelihood. So what that is saying is we're going to maximize the probability. This is what I've been saying about maximizing the probability of observing all the choices that have been recorded. So we then are going to maximize this log likelihood subject to some set of parameters, the betas here. So we can estimate these in our choice model. So for example, here's this case study that we had before. Utility of the first alternative is some estimated constant, alternative specific constant for alternative 1, delta 1, plus the beta of travel time multiplied by the travel time we observe, the difference there, 10 minutes, plus beta of salary times the observed salary. So we've got these, what we call marginal utility parameters for income and travel time, alternative specific constants. We also have one of these alternative specific constants for, sorry, that should say indifferent, this is within different alternative. So what we end up having is different ways for looking at change in choice context. So imagine that I've gone from here to here. There's different ways of doing this, but in a standard choice model, these changes in choice context are almost always included additively. So what I mean by that is, for example, I add the status quo if bias, if alternative 1 is the status quo. So what that means is that I'm more likely, say we've got a positive estimate for the status quo. That means that I'm more likely to pick alternative 1 if it is the status quo, whereas I'm more likely to pick alternative 2 if it is the status quo. So if alternative 1 is the status quo, I'm adding delta SQ to utility 1. If alternative 2 is the status quo, then I add it here instead. Now this looks exactly the same as how we would typically include socio-demographics. So for example, if I want to say, how does a male person make a decision differently, then I would have some constant, typically delta M multiplied by is the decision maker male. So basically what that is saying is that in certain choice contexts, one alternative might be more likely to be picked by men. So for example, a socio-demographic you'd often see is that higher income people are less likely to travel by public transport. And this would be how that is included in the model. Now, psychological changes in choice context are treated mathematically equivalently to socio-demographic changes in the decision maker. So that's what I'm saying here. We've got this psychological change in choice context here, this ordering effect. And then socio-demographics are treated the same, but are they really equivalent? Probably not. And this is where a quantum choice model is going to come in and be different. But sorry, I forgot, I'm going to talk a little bit about the core choice modeling package as well. So this is the main thing that we use to estimate our choice models. It's a R package that was written by my former PhD supervisor, Stefan Hess, and my colleague, David Palmer. It's an open source free package, which means anyone can use it. And there's a huge guide, 200-page plus guide for it. So it's really kind of thorough, meaning that you can readily apply it to your own data sets. And there's many examples of models, including the standard multinomial logic model as described above. And it's got a very user-friendly design, meaning minimal code changes are required for quantum choice models. And I will talk about how I actually do that myself here. So what this actually looks like in terms of code, you'll see there's not many steps to it. So the first thing is this is just loading the data. We're then going to calculate the utility of each alternative. So in this case, we've got a utility for car, bus, air, and rail. There are those alternative specific constants, relative importance of travel time, actual observed values of the different alternatives, the attribute levels. We've got an access time for different modes of transport, and we've got the costs. So we've got the beta elements are our estimated parameters, and then time, access, and cost here are our attribute levels of the different alternatives. So we estimate these 4 different utilities for the different modes. We then use this MNL settings function. This doesn't typically vary, but you can, for example, change the availability. So for example, if some owners don't have a car, then you can change this here so that you can rule out the car option for people who don't own a car. And then there's calculating the probability, and that's just a line you can use as it is. And then you'll have your model. So really, when I use this to estimate a multinomial logic model, the only thing I'm really changing is the specification of the utility, depending on what I've got in my choice data preference data. So that means that what we end up with here is an R function with inputs. So it's the model parameters, the observed choices, the attributes of alternatives, which maximizes some output, the returned probability of observed choices. So really, we've got quite a simple framework here, and that's going to help us when we're then using our quantum choice models. So why might we actually move away from the standard approaches? Our main focus in choice modeling is accounting for heterogeneity across individuals, and most work considers capturing different relative importances for different individuals. But there's been a recent shift towards the idea that some people think in different ways. And there is obviously complexity in how we make decisions. So maybe our models are just too simple to represent this. And there's been multiple attempts at different ways to do this and look at this. So for example, attribute non-attendance, minimization of regret rather than maximization of utility, and the use of heuristics. But these are small steps. So what we want to do is try something further afield. Yeah. So quantum theories, basically. So quantum choice modeling, capturing changes in the choice context. So firstly, I'm just going to give an outline of how we get to where we are with the quantum choice model. So starting with quantum probability, physicists demonstrated that the sequence that measurements were taken affects the final observed values for physical variables. And these are variables are then defined as incompatible with each other as measurements are non-commutative and cannot be made at the same time. This leads to the breakdown of classical logic and led to the development of quantum probability and quantum logic. Now, ordering effects are obviously also a common phenomenon in choice behavior. So the order that we make choices is going to be really important. And your first choice might impact your second. So obviously there's going to be some scope for the same quantum ideas that have been used for physical measurements as well. So quantum-like models are gradually being introduced into psychology as quantum cognition. And they often aim to control for or predict the impact of order effects. So for example, destination and modes, or modes and destination. So do I choose to travel from Leeds into London and then choose to travel by train, or am I choosing to travel by train and then going to London, deciding to go to London? Do I choose an Indian restaurant, then choose to be a vegetarian meal, or do I choose I want to get a vegetarian meal and then think, oh, I'll go to an Indian restaurant. So we can use these models to test the impact of nudges. So for example, asking someone how much they care about the environment before then asking them about which conservation program they will choose. These models are effective for explaining contextual phenomena in cognitive psychology, ordering effects, disjunction effects, two-stage gamble problems. So can we also use quantum probability in a choice model? And what would this actually look like? So we have here a status quo and a new policy. What we have is a belief state that represents where we are in terms of likelihoods of choosing one of these options. This is our Hilbert space, and we've got each choice scenarios is represented by a subspace. Now, each subspace is then created with basis vectors for each alternative. So we've got two alternatives here, new policy and status quo. Crucial difference here with the geometric space is that in the Hilbert space, the vectors have real and imaginary parts. So it's quite hard to draw graphically. So at the moment, this looks like real space, but actually these vectors it could have imaginary components. So the basis vectors are all orthonormal to each other. And this means that, well, at least for choice context where you can choose only one alternative, that means that we've got an indefinite belief state of vector unit length. So this is our belief state. And this means we could choose either policy at the moment. When I actually make up my mind, my belief state collapses and I project onto the vector representing the chosen alternative. So this length of projection here is going to define the probability of choosing the alternative. Now, because they are orthonormal and the state vector has unit length, we know that the sum of the squares of these projections will sum to 1. So this is just Pythagoras' theorem here. Now, of course, because we're in complex space, we want to use complex conjugates as well, just to ensure that our probabilities are real numbers, because we need to work in real numbers for the final outputted probabilities. So why might this work for changes in choice context? Well, here's an example of a nudge. This is not what I've been talking about. Sort of an example. So instead of defining parameters for different contextual situations, how about what I'm going to call quantum rotation through the Hilbert space? So here's this initial belief state. And it might be that I think the new policy is either ethically justifiable or not. Now, if I think it's justifiable, that's answering a different question. So I've got some probability of saying it's ethically justifiable or not. And if I say it is, then I'm then more likely to choose the new policy. So what's happened here is that this original projection length here has increased as I've gone from this original belief state to the ethical answerability belief state. Now, if I instead say, no, that's not justifiable, then I'm going to increase the probability of choosing the status quo. So fundamental differences in these models. So the model in utility space is just this real space here, model in Hilbert space looks quite different. The model in utility space, typically we're assuming that the decision maker is certain and that there's unobserved utility, which means probabilities are generated on the basis of what the analyst doesn't know. But in this Hilbert space, we're actually assuming that the decision maker is inherently uncertain. And probabilities are generated based on the likelihood of the decision maker choosing one alternative or another. So we're saying that actually the decision maker could go either way. And it's only with observed data that we can say a bit more about what the likelihoods was that they chose one option or another. So quantum choice models can possibly then include the underlying deliberation process, allow for interactions between alternatives. They allow for a better understanding of the choices we make, to not have the same simple interpretability of parameters. So that's a negative, but I'll come back to that a bit. And we can allow for calculations of, for example, price elasticity. So this is an important economic output of the model, that we can say, if I change something by 10%, what will be the change in how many people choose something. So that the quantum models still do that. They still give out all of those outputs. We've got two publications that most of this work is based on. And this is just highlighting what those two papers are. So you can go and have a look at this in more detail. First was published in Transportation Research Part B, which is the sort of main methodological and transportation research journal. And the second was in the general choice modeling. And that was about looking at these quantum choice models for moral decision making in particular. So choice modeling and quantum cognition, how can we bring these two together to build a quantum choice model? So I've already talked a bit about how we might do this. There's going to be more to it in terms of looking at specific examples. So here's this classic example, two different alternatives. One is cheaper, one takes less time. So most choice models estimate some sort of utility or preference for each alternative. We need to have some sort of similar concept within quantum framework. So the modulus square of the amplitudes, for example, could be used to somehow incorporate this information. So we need some function required for mapping attributes of alternatives to obtain the modulus square of amplitudes. So before I had model parameters beta and a set of attribute values x. And what we're going to do now is set this amplitude based on some function of these two. So one main example that we use in the paper is to base this function on regret functions. So the random regret minimization model has basically assumes that decision makers minimize regret, and you can define a regret for each alternative in a choice task given by this equation here. So what this is saying is that we're going to compare each attribute, each alternative against each corresponding attribute of each of the other alternatives. And if it's very negative, then so basically if our one alternative looks particularly bad in comparison to another, then we're going to have a high level of regret. Whereas if our model doesn't find that, then this is going to collapse to 0, basically saying we're not adding to regret. So only attributes that are worse than others will contribute to regret. We can then define the amplitudes for an alternative equivalently. So here we've got the same component, this component here, which matches this. And then we can normalize these so that our probabilities over all of the alternatives will sum to 1. So that's our basic quantum amplitude model. We can also extend to have imaginary numbers. So if you look at this, we think, where are the imaginary numbers coming in? Well, they're not there yet. So this is entirely in real space. But we could include an exponential of to theta, estimate theta. So if theta equals 0, we're back into real space only. Theta equals pi over 2, we're in imaginary space only. But of course, theta could be taken on any value, and we could land somewhere in real and imaginary space. And the probability is still easy to calculate. We just need to take complex conjugates now instead. We're just adding in those there. So how does a quantum rotation work? So what we've got is we've got this matrix that is going to evolve, make a quantum rotation through the Hilbert space. So we need the quantum rotation matrix. And this new set of amplitudes is just going to be some multiplication of this transformation matrix and the original set of matrices. Now, there are certain requirements for this matrix to ensure that the belief state vector has unit length. So there's a couple of different options there. So we could use, for example, Pauli matrices, and the rotation matrix is given by the combinations of different types of Pauli matrices. Or we could use Hamiltonians. So this controls the change of the belief state vector according to the dynamics of the Schrödinger equation. So we've got basically we've got a Hermitian matrix here that we can estimate that will tell us how we evolve through this space. So how do we code this in Apollo? Actually, it's really not really many changes. So what we've got here in this case study is we've got the utility specified exactly as we had before. So this is based on Apollo example 7, which is the case study example of minimization. But it's adjusted for a different case study compared to what we have in example 7 here. But either way, this looks equivalent. It's equivalent to, at this point, it looks like a regret minimization model. We then need to normalize these amplitudes, because these are instead amplitudes. So that's what I'm doing in these 3 lines here. I'm going to then generate my rotation matrix. Basically, we're going to have some component of each of the Pauli matrices. So this is what this is doing here. We're finding an overall factor. We're then going to generate a rotation matrix based on this Pauli matrix. We then apply this rotation to certain contexts. So in this case study, we've got what we call a taboo trade-off scenario. Some of the choice scenarios have it, some of them don't. If they have it, then we're going to apply this rotation. So we're going to apply this new matrix U to our previous amplitudes. If not, then we're just going to keep the old amplitudes here. Then I'm going to just calculate the complex conjugate bits there to give us our probabilities. This here will be the probability of choosing the first alternative, and this is the probability of choosing the second. So if our observed choice is the first alternative, then we're going to take the probability of the first alternative. And if it's the second, then we'll take the probability of the second. So we've then got a list here, the choice observed, the probability of choosing the observed choices. So now I'm going to talk about some applications, and I'll just check the time. I've got 10 minutes. So I'll try and cover as many of these as I can in the time I've got remaining. So first case study is exactly what I was talking about before, a left-right change. So cost on the left, time on the right, time on the left, cost on the right, and order change. So the cheaper alternative first or the cheaper alternative second. And we've got a large number, about 15,000 completed choice tasks here. And this is going to be used to get the value of travel time. So basically saying how important is cost relative to time. But what we want to know is, does this order and context make a difference, depending on which one we have. So what we have here is our basic model. We're just going to assume that there isn't any impact, and we've just got our amplitudes as a function of the costs and the times in the choice context. Context shift. So this is the sort of standard way would include these different shifts within a utility model. We could also do that in an amplitude model. We just added on a shift. Context shift captured through our rotations that we've just been talking about. You'd be possibly including these rotations depending on the choice context. So if I've got this case study, I wouldn't use any this case. I wouldn't use any rotations. But if I've got this one, then I'm going to apply the rotation for the order. And if I want to go down to here, then I'm going to apply the rotation left to right. So what we end up with is basically 2 parameters that are going to define these rotations, or 2 parameters that are going to define the shifts, and this might result in a better overall model. So I've included our quantum amplitudes model here, compared it to the standard multinomial logit model, and also a decision field theory model, which is another model I've been doing some work on. And what we observe is that in base case, the quantum amplitude model has the greatest log likelihood, meaning it has the best model fit, and therefore best predicts the observed choices. And this is quite a significant difference. We're seeing this is would substantially reject the null hypothesis that the models are equivalent, and the quantum amplitude model is clearly better here. But how do we best capture these context shifts? So what I'm looking at here is the log likelihoods improvement. So if I just do an additive shift to the logit, DFT, or quantum amplitude model, I'm getting an improvement of less than 10 units model fit. But by using quantum rotations, we get an improvement of 11 units, which means that in this case, the change in choice context is best captured by quantum rotations. So yeah, this is a sort of first suggestion that these are a good way to capture context changes. Second choice context is looking at proposed new transport policy. Various different things are going to happen, and do you support the policy or not? For example, there's a new road being built where which will result in less tax, less travel time, but potentially more injuries. And this has been termed the taboo trade-off on data set, because if a decision maker can choose to save money, decide that it's ethically justifiable or not. So what we're going to do here is we're going to use this Hamiltonian operator to apply a rotation if we have this taboo trade-off. So we're basically saying, if there's a taboo trade-off, someone's going to have to justify whether the choices are ethically answerable or not. So they're going to make the choice from a different viewpoint to the original point. So they're making the choice from here for most choice contexts, but if there's the taboo trade-off, they're going to be deciding whether it's ethically answerable or not. And what we again see is that our best model is the one that uses this rotation. So a little about the log likelihoods, which are sort of meaningless numbers at this point. What this translates to in this case is that the basic model has an average probability of 63% of finding the observed choice. So basically, that's saying my model is 63% accurate. This rises to 64% in the final model. And though that might sound like a small change, this could make a huge difference in terms of the accuracy of wide-scale, large travel planning things, for example. That 1% could be really crucial. We can then also add quantum models with imaginary parts, and this makes further improvements to our models. So we're observing that working in imaginary space, the Hilbert space makes a difference, and we can reject the null model with only real components. What this looks like in terms of model output, here we've got the 16 different choice scenarios. We have observations of how many people accept each choice. And our quantum rotation model finds really closely captures this. So that it's getting very close to what we actually observe in the data with not that many parameters. I'm a bit short of time, so I'm going to skip this final data set and just talk about a couple next steps and conclusions. So there's different ways of different things we can do with our quantum models. So for example, we're talking about indifferent alternatives. For example, so this is one thing we could do differently, is maybe treat indifferent not as a completely separate alternative. So indifferent maybe actually lies somewhere between status quo and the new option. So that's one future direction. And the quantum framework should still be well placed to deal with such intricacies as it captures interference effects. So this is actually, what I'm saying here is that the quantum models are much better placed than standard models for capturing that fact that indifferent is actually not really a different alternative. Other directions, quantum choice models for nudged choices. So can we actually observe how people change their behavior if someone pushes them towards other alternatives? Extensions to repeated choice data, for example, can we capture learning effects? Large scale moral data. So I'm referring to, for example, the moral machine data set of MIT, which is well worth looking at if you have a chance. We can also make a return to experimental psychology. So how would the models I've developed here perform in these settings? So some final conclusions. Quantum choice models give good model fits, meaning they accurately represent observed choices. They're simple to run and estimate, and although I've given only a really brief overview here, I'm always more than happy to talk about coding quantum choice models. So please do drop me an email if you're trying to code a quantum choice model and you want to know how to do this within Apollo. I can go through these steps with you and explain how to do that. Our rotation matrices appear to accurately capture changes in perspective. This is a really good thing. I mean, there's multiple different contexts which we'd like to apply this to, and this is something that we're hoping to do. This is one of the next things I'm hoping to do. It also works well from changing from best to worst choice. So for example, if you're choosing your favorite alternative or your least favorite alternative, the quantum rotations work well for that. Are they a particularly good fit for moral choice. That was one of the things we're looking at in the second paper, and the evidence is not really, because quantum choice models always seem to do a little bit better, and it's not particularly evident that for moral choice data there's any differences. And with that, thank you. And just a little advert to the Apollo choice modeling package, which it is very, very useful and has allowed me to do all of my research. So thank you very much for listening.
Thank you very much. This was really a very rigorous presentation, we should say, and you covered quite a few bits, starting from the history of quantum-like modeling to applications, and also contrasting with the standard choice models. Definitely, I personally have quite a few points, but I will definitely we can exchange over mails on this particular attempt. Here, before I go to the other questions, if I may just add a couple of points. The one thing is that when you're talking about orthogonal projections as your most important kind of basic model, because that is the basic Hilbert space model, we could also think about positive operators. Positive operators are like bit more flexible. So for non-orthogonal conditions where the basis states are not orthogonal to each other, or there's some kind of noise in the model, then perhaps POVMs, positive operator value measures, they are supposed to work better. So there have been some kind of good evidence for that. So that may be one point. And the other...
Can I just check what you said?
Yeah.
Non-orthogonal.
Yeah.
So basically that would mean you're assuming that you can choose more than one alternative.
Yeah.
Okay, and that's obviously important, because some choice context I would walk to the bus station. So I'm choosing one. So that's
that is one. And the second thing is that also when you are deducing your rotation matrix, there you are using the Hamiltonian operator. So at times we have seen that in financial modeling, for example, there can be non-Hermitian operators also, which might be more applicable. And there are ways of dealing with non-Hermitian Hamiltonian operators. So you might take a look at that. Carl Bender, for example, has worked a lot on non-Hermitian operators. I can say,
Does it? Sorry, how does it? Because the reason we have the Hermitian operators there is to preserve normality, so that the probabilities of alternatives are always.
Yeah, but say for example, in various decision-making scenarios, there is a lot of like informational problems. Say for example, information asymmetry and leakages of information from. So in those areas, in those cases, non-Hermitian Hamiltonians may help better.
Okay.
Yeah, so these are the 2 points I'd just like to mention, but there are many other interesting issues which we can talk about later. So I'll be then we'll be more than glad to open up the floor to the other questions, please.
Can I have a quick question, if you don't mind? So, with my little background and also little experience, especially from the healthcare field, we actually kind of, follow you guys, in transportation and also environmental science, choice modeling. Just kind of wondering about, you talk about the quantum model, but you haven't mentioned about, how do you decide the choice set? So can I assume that you basically using the, certain kind of efficient design when you decide the choice set?
Yeah, so the stated preference surveys that we use are usually always created with some sort of efficient design. So all of that stuff is exactly the same, really. That doesn't actually change when moving to the quantum choice model. So basically what you have there is you just be using the same choice sets and all of the same rules apply. I
Okay.
guess. Yeah.
Okay.
Now, I think there'd be, I mean, hypothetically, you could look at different case studies where you might, if you had dominated alternatives, you might have different implications from quantum choice models compared to standard models. But if you want to really look at behavioral outputs from the models in terms of what attributes are important, and you really want a sort of solid data set, then all of the same rules will apply, basically.
Okay. Yep. Thanks.
Mm-hmm.
Hi, I'd like to, can I ask a question?
Mm-hmm. Yeah, please go ahead.
Hi, thank you for a lovely talk. And, I mean, you explained the mathematics so intuitively. It was wonderful. But I'm talking from a applied researcher's point of view. And I was just thinking in terms of, I mean, the sort of inputs that go into these models. So of course the Apollo package and all of that's nice. I mean, you put in the inputs and you use the package and you get the outputs. I was just wondering, like, this survey data that you collected. So this ordering effect. So basically, different people got randomly selected for different orders. Can you explain that a little bit?
Oh yeah. Okay. So, yes. So people didn't face repeated choice tasks. So for example, if in that case where I showed the 4 different possibilities, people would only have seen one of those. But I think what we had was everyone either had cost on the left or cost on the right. But because everyone was presented with 10 different choice scenarios, the cheaper alternative could sometimes be on the top or bottom for each different person. And so some of it was kind of within participant, but some of it had to be different. And because it would have been confusing to the respondent, it would continuously change the choice context. So basically of those 4 different contexts, everyone saw 2 across the different choice tasks they completed.
So sorry, can you just repeat that? So everybody saw 2.
Everyone would have seen 2 of the different choice contexts across. Yeah. So for one of the effects, we didn't really look at the differences in terms of within or across participants. So one of the cases we could do that, but the other we wouldn't be able to, because it was of how we've collected that data.
Right. I mean, the reason I ask is, I do research on, do survey research in very, very sort of difficult circumstances.
Mm-hmm.
And typically the reason is, if, for example, you're interested in choice between political parties and so on, in a sort of a conflict affected area. And there's a reason we keep these surveys simple, so that, ultimately we end up running multinomial logits, not because we want to, but because, that's it's the quality of, you can't ask, sort of very complicated or, that's that kind of stuff. So that is why sometimes, we're stuck with methods because we can't really, the input side is very limited. So I was just trying to get a sense of.
Yeah. So I guess what we do here is to control for a possible effect of the stated preference design. So the ordering effects there, that could bias our results if we don't account for the fact that cost or time being on the left might have an impact. So in some case studies, we want to try and eliminate that left-right bias, because that's not helpful moving forward. Now, in some cases, it might actually be good to know, because if you want to nudge people into making a choice, you start putting what you want people to choose on the left. And there's plenty of examples of, for example, supermarkets changing the order of things to nudge people into choosing the things they want them to choose. But that's slightly different if we're thinking purely as a modeler who wants to understand what people are choosing. Then the more biases we can eliminate, the better.
Okay, No, thank you. Thanks.
Yeah.
By the way, you just sorry, Shudip, one more question. You said that 1% was a fairly important thing in transport research, but were you expecting more, even a more substantive change, more than the 1% effect? Or you were happy with? I mean, this is good enough.
No, it's because the model was very significantly. Basically the null hypothesis were very significantly rejected, but the models were the same. So in terms of other ways of comparing the models, is very significant.
Okay.
The overall implication is not something that we'd really use to compare models typically, but that was just to give you some people a better idea. They weren't used to seeing log likelihoods, for example.
Okay, thanks.
Yes, I think that more basically, perhaps we might clarify that the uncertainty that you have been talking about in your model, the fundamental uncertainty, that is perhaps the most important point of departure from the other standard models. And that is what is being captured by the so-called superposition principle on the Hilbert space. So that is the main point of departure from these models and others. I'd also be quite interested to see some interference effects. I mean, perhaps, because quantum probability model, the most important thing are the interference effects. Yeah.
So, let me just check. Did I talk about that in the final example? Yeah, so sorry, the example I skipped over, I actually talked a little bit about that. So let me just share screen again and I can just talk briefly about that. So let me get this up. So can you see my screen again? Yeah. So this is the rotation matrix output from the final case study I had. And what we can see here is that there is more of an interference between options 1 and 2. And this is looking back at that case study where we had the 2 different alternatives or the indifference option. So what we see basically in this case is that there's much more interference between the 2 sort of numerical alternatives compared to the indifference one. And that's something you could expand upon in terms of looking at how the different alternatives interact and how interference between them. So, for example, you might, if you had quite a lot of alternatives, say 5 or 6 alternatives, you might see that there's some sort of ordering effect in terms of how you read the options, and that alternatives that are close together would interfere more with each other, basically. Like that would be an example you could look at. So yeah, there's more that you could do.
And perhaps finally, I would also like to just mention this, if that helps you. Andrei Krenikov, you know about his research. So he's one of the well-known people here. Andrei Krenikov and I think Ozawa, they have come up with some theoretical models of kind of combining various effects like order effect as well as response replicability kind of effect. That is also quite well known. So how to combine these two or more effects in one particular model. So perhaps you might have a look at that, and perhaps how your model responds to that would be very interesting to see, because and that is the theory of quantum instruments, as as it is well known.
Can you give me an example of what?
Say for example, say for example, 2 different effects. One is the order effect that you have already mentioned in your research, and the other one is the response replicability effect. Say for example, once the particular question is asked and then another question is asked, and then you have some time interval in between that. So how then the respondents would choose. So if there's a kind of, so and since in your model you already have the Schrödinger evolution using the Hamiltonian, so in that case perhaps it might be interesting to see how to combine different types of effects at the same time. And Andrei Krenikov has a very interesting paper on that. very recently published. That's it.
Okay, thank you. Thanks.
Thomas, if I might, I just have a quick question on the applicability of these choice models
Mhm.
to chaotic transport situations. I'm thinking more about developing country situation.
Yeah,
If
okay.
you've been to Delhi, or if you've been to Mexico City, or indeed Lagos, or Karachi, and you can choose or Manila.
Yeah.
It's a little different, you know, from London or Toronto or New York or Auburn. And I wondered about the applicability, because I would hope that Sudeep would be working with you for us to begin to use these models to inform decision making and transport policy in India. Well, yeah, would it work?
So
it should work, right?
Yeah. So this is actually a key research interest. My direct manager at the Choice Modeling Center, Charisma Chowdhury. I grew up in Bangladesh. She's got a lot of contacts there and does a lot of choice modeling work with people there, and that's one of the main lines of work is sort of transferability of models across very different contexts, and there are just a number of different things you have to think about in your model. So there's one PhD student in our group who's looking at how people allocate their time across the day. So it's the choice modeling application is you know, how do people allocate their time? And of course, people in Bangladesh do that very differently to people in the UK. And there's a lot more, for example, one major difference is that there's a lot more people who have their older parents living with them in Bangladesh. So there isn't the same care system that the UK has, where we have sort of old folks homes or places for the elderly. So that means that your activity patterns are very different, because you've got someone at home, potentially you're looking after some elderly relative, and that is a kind of clear example of a sort of social demographic difference. But then of course there are also the sort of more physical differences of like a lot more congestion in cities, for example, like ones you talked about. But in all of these cases, it's a case of trying to understand the choice context first, and then having as realistic if you're looking at stated preference data, as realistic stated preference choice task as possible. So if I'm just looking at choice time and cost as my key example, if I'm asking people that question in the UK, that might seem reasonable. But if I ask that in India, that might not look reasonable, because travel time is going to vary massively depending on how bad the traffic is. So actually, a more key component to my stated preference there would be time variability. You know, that's a sort of key example. I guess you've got to adapt to what the data you collect according to the context. And in some cases, there's some bits that are transferable. So you might have certain distribution of people in terms of how people how important they say some element is. So distribution you might have for the time might be the same in the two different places, but it's shifted slightly, or it's extended slightly. So it might be you've got just a different median, but you've got the same.
So instead of having 2 or 3 variables, cost, time, and so on, if you were to have, I guess it boils down to, if we had multiple variables, multiple choice questions, so we had 8 to 10 variables in a much more complex and chaotic situation, in principle, the model might become a bit more complex, but it should work, shouldn't it?
Yeah, absolutely. And there's the most complex models are, even for simple situations, are kind of quite advanced, because understanding heterogeneity of preferences is such a key thing. So I guess the differences in in some contexts, you might have put more emphasis on explaining socio-demographic differences, whereas in others, you might need to think about the actual dynamics of the situation a bit more. So that might come in first. And there's plenty of research on that, I believe.
As far as we see that the say, for example, as Naresh was asking on that multiple questions and dimensions, so that interaction basically can come into the Hamiltonian operator that you're building, because we can have interaction Hamiltonian part into that.
Yeah,
So
absolutely.
then we should be able to look forward to a dynamic collaboration between our two institutions.
Okay.
Yeah, I would hope that Sudeep will take this seriously and lead it forward. That'd be great. Thanks.
Thank you very much. This was really a very kind of rigorous and kind of enriching presentation. Yeah. So I think we have our dean with us, Professor Sudarshan.
No, I just wanted to say thank you, and picking up Naresh's last comment, we should, establish a firm partnership with Thomas and his colleagues. So let's go ahead with that, because this is all exploratory and on the frontiers of possibilities, and we should be open to working on that with full steam ahead, as it were. Thank you.
Thanks, Thomas. Good to see you as
Thank
always.
you very much. Thank you. And thank you everyone for supporting this particular talk, and the IT department also. That was really a great support. At times we find problems with sharing screens, etc. So thanks a lot, everyone.
Thank you. Thank you.
Thank you, Sudeep. Thank you.
Thank you.